Welcome everybody to the science behind Netflix recommendations. My name is Jelani. I am your host and also the marketing program manager for data science. So any questions regarding your admissions process, um, anything outside of like the actual curriculum, I can probably answer for you. I can even answer some things to do with the curriculum. Um, we're really excited to have you here. This is one of our most popular workshops. We're bringing it back. Um, and we're really excited to have you today. So just a few things. For those, I see a few people just joined. So in the chat, make sure to hit the panelist button. It's a drop down to panelists and attendees. When you click that, now everyone can see everyone else's comments in the chat. Just don't want too many like repeat questions, and you might ask a question that someone else has. We will be taking questions during and after, probably mostly after. So if we don't get to your question, during, please don't be mad at us. We're gonna get to it. And anything else? I think that's it. I think we can go ahead and just jump right in. Ish, how you feeling? Want to jump in?
Feeling good. Yeah.
All right. Well, Ish, I'll let you introduce yourself.
All right. Hi, everybody. My name is Ish. Let's see a little bit about myself. I've been working at Flatiron School for a little bit over 2 years now. And right before that, I actually did the data science program. So yeah, come a long way since then, almost close to 3 years with Flatiron School. And yeah, had a lot of experience with the data science program. Super excited to share with you all today this workshop, the science behind Netflix recommendations. Recommendation systems is a part of our curriculum, a little bit towards the later half because it is pretty intense. We have a couple math slides that we're going to see, but not to worry. I will break it down as much as I can, and I'll let you know what are the main concepts to be aware of, but we're not going to be doing any really intense stuff today. But yeah, recommendation systems was a part of our curriculum. Fell in love with the way that recommendations are actually being generated. I did a lot of research after the program on like how different companies and different platforms are making their recommendations, and that like sort of I guess became my thing. And so I'm really happy to share all of this material with you all. I will be having a couple like breaks for questions, so leave your questions in the chat. I guess I can also see the chat, or if Delaney of you are following chat and you see like some good questions, let me know.
Will do.
But yeah, let's get into it. I've broken this down into a couple sections. So first of all, we're gonna do a very like overall conceptual introduction to recommendation engines, and we're gonna talk about 3 main types. And then we're going to go into more specifically how Netflix makes recommendations, or I should say how through my research, I suspect Netflix makes their recommendations. Their algorithms are not publicly available. I also do not work for Netflix. And then also at the very end, let's see, does this come up here? Yeah, at the very end, I'm going to walk through some coding examples just to show you all how someone would use a library in Python to build a recommendation engine. I just saw in the chat that someone asked if they can get the tutorial. I believe in the email that will be sent out with this recording, you'll get a link to all of the material that's being shared today. All right, so part 1, an introduction to recommendation engines. So there are many different kinds of recommendations, but we've mainly broken it down into 3 main kinds. But before that, let's sort of think about why we need recommendations and what are some examples. There are some very obvious ones, like Netflix is a recommendation engine. Spotify has a pretty great one as well. Pretty much anything where you're consuming content. I think one of the lesser popular examples of recommendation engines are ads. I mean, they're annoying, but if you are on Facebook and Instagram, and I personally now pretty much only shop off of like Facebook and Instagram ads because they're just so well targeted to me. Those are also ads. Those are also recommendation engines. They are built off of the same kinds of algorithms as recommendation engines. So super cool. The 3 main types of rec engines we're going to talk about today: non-personalized, content-based, and then collaborative filtering. The first 2, we're going to gloss over and talk about like kind of how they would work. But the one I really want to focus on, which is actually one that Netflix really popularized, is collaborative filtering. So we'll talk about that in a little bit more depth, and we'll go into a little bit of math related to that. Okay, so non-personalized recommendation engines, it's as straightforward as it sounds. I saw Delaney, you mentioned YouTube. I'm a big fan of the YouTube recommendation algorithm as well. But in the case of a non-personalized recommendation engines, I don't know when the last time anyone did this, but if you go onto YouTube as a completely brand new user, you still get a bunch of things recommended to you. So this was just me on like incognito mode, opening up YouTube. And okay, this was also from like 2 years ago, but what was being recommended? Basically the things that were trending. And the idea of non-personalized recommendation engines is you imagine at this moment in time, anyone who's a brand new user going onto YouTube, this is probably what they're going to receive. Maybe filtered by like location, perhaps filtered by if Google has the information on your age or things like that, sure. But for the most part, there's not too much personalization going on here. Basically, new user, what are the top trending videos right now? This person is very likely to click on one of these videos. So it might seem very simple, but it's actually used more than you would expect. First of all, it's like when you don't have any information about a user, right? Like if you are, I don't know, if you're from Mars and you come onto Earth and you're like, I want to use YouTube, they have zero information about you, they will use a non-personalized recommendation engine. If you are a brand new company or store and you want to push products to customers, maybe instead of trying to figure out what each individual person would like, maybe you push your most popular product. Maybe you push the product that you think will get you the highest ROI. You can definitely do that as well. So non-personalized recommendation engines, very simple. You literally just pick which one you want to recommend out of like your inventory. But there are a lot of, it's highly underrated, a lot of use cases. All right, so let's talk about the next one, content-based recommendation engines. So when you think about content-based recommendation engines, you start to get a little bit more personalization, and content-based recommendations will be kind of similar to actually even more recent. If anyone's on TikTok, if you start to like interact with anything that's like in one specific realm, for example, if I'm really into like cooking TikTok videos, you realize that all of your future TikTok recommendations are all going to be cooking videos. That I think, I haven't really looked into TikTok's recommendation algorithm, but it sounds like it's very similar to a content-based recommendation engine. So what a content-based recommend engine does is it makes recommendations based on an item's features. And what features are, let me pull this up in a bit. Imagine this is Netflix database of movies. So we have a bunch of movies, movie 1, 2, 3, 4, 5 for now. And every movie has different features, which is the data science word for characteristics. So a movie can have many different characteristics, many different features. So for example, maybe every movie does have genre, maybe multiple genres as well. You have who's acting in the movie, who directed the movie, what year it came out. Maybe they also have their like IMDb, Rotten Tomatoes scores. And the whole idea behind content-based recommendation engines is if you know that person A likes item 1, you want to recommend person A items that are very, very similar to item 1. That makes sense, right? So let's say I'm on Netflix for the first time and the first 5 movies I watch are all horror movies. Chances are, if it's a content-based recommendation engine, you're going to get recommended a lot more horror movies. And how exactly does that work? If you have all of this information, and let's say we just have information on movie title and genre, and let's say horror is one of the genres that we have. Let's say in this small movie catalog, we have horror movies, comedy movies, and I don't know, dramas, for example. And let's say movies and the movie title and the genre is all we have. If we know that I have seen 5 horror movies and watched the entirety of these horror movies, very likely we want to compare and see, okay, what other movies are also horror movies? We will recommend that. And this can be expanded into the other features as well. Let's say for horror movies, I specifically like horror movies with, I don't know too much about horror movies. I don't know why I came up with this example, but let's change it. Let's say I really like the Avengers. Let's say I really like the Avengers movies, superhero movies. And then I've seen like all the Marvel movies. And let's say Netflix has all of these movies on their catalog. I've seen all the Marvel movies. What should they recommend next? They'll probably look at genre, okay, different genres, but perhaps they're going to look at different actors, for example. So in the Marvel movies, they've got Robert Downey Jr., they've got, who are the others? Scarlett Johansson. Perhaps they can also use those as features and look for what other movies are Robert Downey Jr. in, what other movies are Scarlett Johansson in. And so doing that kind of comparison between the different items in your catalog, that's how you do content-based recommendations. Before we go on to talk about the next one, let's talk about some pros and cons of content-based recommendations. So this is a pretty funny story. A couple years ago, I wanted to get into plants. And so off of Amazon, I bought a plant, but then in like less than a month, my plant died. However, I'm not a huge Amazon user. I don't use it too much, but because like one of the few transactions they had from me was me buying a plant, they kept on recommending plants to me. And it was extremely heartbreaking for me to just see like a bunch of like plants getting thrown in my face. So that's an obvious pitfall of a content-based recommendation engine. If you don't have varied information about a person, you start to really pigeonhole every user. So yeah, that kind of sucks. Let's see, I have some other notes here. Yeah, so for example, another unpopular opinion is I actually really like Nickelback. I'm a huge fan of Nickelback and their awful music. I think it's fun. But if someone was to make content-based recommendations, they would just recommend me music that sounds like Nickelback rather than other music that people hate. So if you just compare it that way, those are some maybe pros, maybe cons. Maybe you really want to get pigeonholed as like the horror movie person, then sure, content-based recommendation works. All right, so that's content-based recommendation. And just let's talk about the next one. And this one will go into a little bit more depth because this is the one where like we have some real like machine learning data science coming in. So collaborative filtering is a umbrella term for any sort of algorithm that makes recommendations for items based on the ratings of other users. So there are many different ways to do collaborative filtering. If you like look up collaborative filtering algorithms on Google, you'll get actually a bunch of different ones. But the most popular one that was actually popularized by Netflix, and I'll go into that story in a little bit, is called singular value decomposition. So this gets a little bit complicated mathematically. If anyone is into math, it combines calculus, linear algebra, as well as machine learning, which are like the processes of gradient descent. I'll get into that in a little bit. The whole idea behind collaborative filtering is, for example, I like the show Friends. And if I have another friend that also likes the show Friends, it's pretty likely that I will like whatever shows that friend likes. So similar interests. And what's new here, what's being introduced with collaborative filtering that content-based algorithms didn't have, is you actually can compare different users on your platform. So that's an added dimension where you're looking at, user patterns. So SVD actually has a really interesting backstory. Back in, I think it was 2007, Netflix used to run this yearly competition called I think it's literally just called like the Netflix competition, where they actually take a bunch of anonymized data of like users and movies. And the only information that they had was what each user rated each movie. So you would have maybe like, I don't know how big their data set was, but maybe you had like 1,000 users and all of the movies that those 1,000 users watched and rated. And back then Netflix used to be on like a 1 to 5 rating, I think. I think now it's just like thumbs up, thumbs down, but you can kind of apply the same concept. So story behind that is Netflix at that time did not have this recommendation algorithm yet. It was someone who actually entered their competition, a guy named, his name is Simon Funk, in 2007, came up with this idea. I think he was a mathematician or just someone very involved with math. Came up with this idea for this kind of algorithm. And it's now one of the leading algorithms that are being used for collaborative filtering methods. So yeah, this was back in 2007. I think he won a bunch of money. I don't think he ended up working for Netflix ever, which is funny. But yeah, that's the backstory. All right, so let's get into the algorithm. It's going to be a little bit intimidating because there are going to be a bunch of numbers on the screen, but hopefully through this. And yeah, any questions that you all have, throw them in the chat. I do see the questions come through. If I see a bunch of like question mark faces, I will pause for a little bit. Okay, let's get into it. Before we start, how do we set up this problem? As I mentioned, in this competition, in the Netflix competition, the only information that they had were just the ratings. They did not have any information about individual movies, like not like we had for content-based recommendation engines. We did not have their genres. We didn't even have their directors, actors, none of that. The only information that we had were ratings. And so the way that in this problem, we're going to set up our data is in what's called a utility matrix. So this is what a utility matrix looks like. Honestly, the orientation of this doesn't really matter. Here, as an example, you have a bunch of users. Every row is going to be a user, and every column is going to be a movie. So this is how utility matrix usually starts, right? Imagine Netflix has like what, millions and millions of like TV shows and movies, and a bunch of users as well. And so how the utility matrix is usually set up at the start, there are a lot of blanks. So for example, here we have user one. User one has only seen movie one, rated it a 1, and has also seen movie N and rated it a number 3. And then we have all this other information. Because every user probably hasn't seen every movie, there's going to be a lot of blanks in this utility matrix. And the whole idea behind collaborative filtering is we're trying to fill in these blanks in some way, and then recommend the next highest. So for example, for user one that rated movie 1 a 1 and rated movie N a 3, the next highest thing that they hadn't watched yet was movie 2, which was a 4. So therefore the recommendation engine would be like, okay, let's give user one movie 2. So the algorithm we're going to talk through today is how to fill in these blanks. Also, just to mention, this is not the only way that you can fill in the blanks. There are other methods, but this is the SVD, singular value decomposition method. All right. Yeah, why was that a 4? We're going to get into the math of why that's a 4. Okay. So
real quick, Ish.
Yeah.
We had one question here. Because you bought this, people also bought this, like on Amazon recommendation, be categorized as collaborative or content-based, or both?
Ooh, that's a good question. Because they had the phrase other people also bought, as long as they're considering other users, you can probably say that it's collaborative filtering.
Thought so. All right, cool.
Yeah. If it just said like similar items are, then that's more content-based. Yeah, that's a good way to distinct between the two.
Yep.
Cool. Any other thoughts or questions? Let me see. I don't think I saw anything very specific in the chat either. Ooh, what kind of recommender system would it be if it wasn't ratings involved? Would it be content-based? Probably. Actually, something that's pretty interesting that I've like read a bunch of stuff about is people try and proxy ratings. Like for example, let's say like Netflix or other streaming services didn't have like a rating system. They would try and think of a way to gauge what you might have rated it, maybe based on like how much of a movie you watch. Maybe in a 2-hour movie, if you only watch like the first 20 minutes, you probably didn't like it. And so they would sometimes find a way to mimic ratings.
That's interesting.
Yeah, super cool. Regarding content-based recommendations, is there a way to have it not be as aggressive to pigeonhole users? Oh, that's a good one. Yes, there is this whole field that unfortunately we will not get into today, but there's this whole, there's this general term called regularization. And that's the whole idea behind making sure that a model doesn't, basically a model doesn't pigeonhole to any specific user, any specific user base. So there are usually methods set in place to make sure that you're not being recommended like the extreme of all extreme like horror movies, for example.
I got one quick question here. I actually think it's kind of interesting. Do recommenders only use one or the other? Is there any way to kind of cross-pollinate between collaborative and content?
Ooh, very, very cool. Yes. So Definitely. I would say there are a couple libraries. I forget if I talk about it later, but yes, there are some libraries that allow you to do some sort of hybrid between collaborative filtering and content-based. Some of the simplest hybrid models, you would just have 2 models and then see what the rankings are of like your top 10 most recommended coming out of each model. And you find some way to like aggregate that list of recommendations. So yeah, hybrid ones definitely do exist. I think I myself have also built a couple hybrid models. Cool, exciting. These are awesome questions. All right, let's talk about collaborative filtering and this kind of intense math. So here, what we have here is a very, very simple utility matrix. So for the sake of this example, we're going to imagine that we only have 4 users and we only have 4 items. And the only blank that we have is user 1 and item 3. So in this very simplified example, all 4 users and all 4 items have been rated aside from this one. So the idea, what we're going to try and do here is figure out what the estimated predicted rating is for user 1 and item 3. So for utility matrices, and this is our utility matrix, if anyone is familiar with linear algebra, and it's okay if you're not, but if anyone is familiar with linear algebra, SVD, which is I think like material in like the last 2 weeks of a college linear algebra course, so don't worry about that at all. SVD is the process of breaking up a matrix into its components. Another word for it is matrix factorization. And factorization, if you have PTSD from like algebra math, if you remember, if you had like a quadratic equation, like x squared plus 2x plus 1, and they have you like split it up into x plus 1 times x plus 1, that was the process of factorization, is basically representing one thing as a product of 2 things. And so that's kind of what that's kind of similar to what we're doing here. We're trying to represent the utility matrix as a product of 2 component matrices. So what we have here, we're going to have an item matrix and a user matrix. And essentially what we're going to try and do, we're trying to figure out, okay, we have an item matrix and a user matrix. How can we multiply these together to create our utility matrix? More details to follow. But if you are familiar with matrices to some degree, you know that this question mark over here will be, when you multiply these matrices out, will be affected by anything under I3 here and anything under U1 here. So that's like the linear algebra part. Okay, so to move on, we actually have to talk a little bit about gradient descent, which is basically what machine learning is built off of. So machine learning, I know it sounds kind of scary, especially for those of you who haven't like experienced or learned about machine learning yet. Machine learning is something that we teach like right around the halfway point of our course. And it's really, really interesting. It's actually very, very elegant. The way a machine learns is, let's say I want to figure out, maybe we want to figure out, okay, this is not exactly how it works. So let's say I want to train like a computer how to play chess. When I'm training a computer on like how to play chess, I'm not even a chess player, so I'm not sure if this makes sense or not, but the computer starts off not knowing how to play chess at all. So it's going to keep making like moves that don't make sense. Maybe you can code in, all right, this piece can only move a certain way, so on and so forth. But over time, it learns through its mistakes. And what usually happens and how it like can quantify these mistakes is there's usually some sort of like mathematical measure of how bad it's doing. So let's say when it starts off, it has a score of like -5,000 because it's just a really, really bad computer. And the idea is the computer is going to slowly keep trying out different things to get its score higher than -5,000. So over time, it's going to improve. That's more dependent on like the way it's designed. But over time, the idea of gradient descent is going to improve its score over time. And then you have a computer that can beat people. That's kind of what we're going to do here. For this particular algorithm, we're going to try and recreate our utility matrix. So it's kind of difficult to break up a matrix into a product of its components. So therefore, we're just going to do it the other way around. We're going to just figure out what component matrices make up this utility matrix. And so to start, like most gradient descent procedures start, you usually start with some initial poor values. You just start with bad values, and we're just kind of figure out how we can make it get better. So to start, let's initialize our component matrices with 1. It's probably not going to end up being 1 at the end, but it just needs to have some sort of starting point where we can then figure out how to improve. So it starts off as everything as 1. If you know matrix multiplication, if you multiply these two together, it becomes an entire matrix of 2s. If you don't know matrix multiplication, also doesn't really matter too much. But basically, when you multiply these initial values, it creates this utility matrix of all 2s. And like I talked about before, with that bad chess bot computer, it had a score of -5,000. So how can we think about, how can we score how well our utility matrix is doing? So in a kind of similar fashion, let's assign this score. And in this case, we're just going to use RMSE, which stands for root mean squared error. So what we're doing here is we're going to figure out how close is this recreation of a utility matrix to our original utility matrix. So this 1.75 that I got here is really just the average error between each rating. So you see how like user 1 item 1, here we have, I mean, for these are all 2s, but here for user 1 item 1, we have 4. The error is going to be 2. For user 2 item 2, sorry, user 2 item 1 here, the actual rating is 2. At this point, this is actually correct. So the error is 0. For this guy, the error is 1. For here, the error is 3. So it averages out to roughly 1.75. So that's going to be our measure of how poorly our model is doing at this moment. Over time, the goal is to get this RMSE number as low as possible. I'll tell you now, like the RMSE will never go down to 0, but we're going to try and get it as low as possible. All right, so how do we do that? If you know, like I think this is calculus 1, but doesn't really matter either. So the way that gradient descent works for this case is you're going to keep changing up values to see how it improves the model. So let's start with changing up values in the component matrices here. So all of them are 1s. Let's figure out what's the best value for this particular x in the corner here. So with this particular x in the corner here, if we just use this as an unknown value and we re-multiply out our matrices, you end up with a bunch of x plus 1. So if you do the matrix multiplication between these two, with this being x, this becomes x plus 1. Now, because we have x plus 1s here and we have 4, 2, 3, 5 here, we just have to figure out what's the best value of x such that the error between these 4 are as low as possible. You can do this automatically in Python. They actually have it built out for you. But if you want to get into the math of it, you're basically taking a first order condition, or you're trying to find the minimum. So here what we're doing, you see how we have 4, 2, 3, and 5, which correspond to these values here. We're going to minus x plus 1, square it because we're taking the squared error here. And then basically when you minimize this equation, it actually finds that the best x at this moment is 2.5. So, okay, the best x is 2.5. Let's just see how that improves our model. With x equals to 2.5 here, when you multiply this out, this whole row becomes 3.5. And then if you compare 3.5 to this row, and if you compare these utility matrices at this point, the RMSE has actually gone down to 1.58, just by adjusting 1 out of 16 values here. So previously it was what, 1.75? Just like that, we've gotten about like let's see, how much improvement is that? Like a 20%? No, I'm not going to do percentages right now. We've improved on our model. And so what's going to happen, and in Python, this is all done for you in the back end. What this is going to do is going to repeat this same process of finding out the best values here for every single one of these ones. And not just once, but over and over again. Because you imagine, like, after you change all of these values, maybe 2.5 isn't the best anymore. So you're going to keep changing values over and over again. You can actually tell it how much or how long you want your model to be training. And at some point, it doesn't even matter what these are anymore. Like in Python, it really doesn't matter what these are because those numbers don't really mean anything. But at the end, you end up with a matrix that kind of approximates your utility matrix as close as possible. So this was, I think, after running this for like, I think I only ran this for like 10 seconds. And in 10 seconds, it lowered the RMSE down to 1.15. Actually, no, this was not even 10 seconds. This was immediate because it's such a small matrix. But anyways, based on this, we have an average error of 1.15. That is a lot better than 1.75, what we started with. And then you see here, we have this estimated value of 3.7. So just like that, we have filled in this blank with 3.7. So the predicted rating for user 1 and item 3 is 3.7. Cool. So that is the algorithm. That's actually how this guy, Simon Funk, was able to win the Netflix competition. I think he predicted everything with like a, I don't remember how they calculated accuracy, but I think it was cited that he had like a 95% accuracy on guessing what people were going to rate movies on Netflix without any information about the movies, which is, I think, pretty incredible. But yeah, that's the intense math. Before we like move into the code, I do want to talk about some pros and cons. So first off, super personalized. The ratings are very, very heavily personalized for every user, and it's taken into account like maybe if like two movies are similar by the numbers, but very different based on how people receive them, you can actually account for that using a model like this. So very, very personalized. Downside, it is a little bit computationally heavy because as you can see, we did a lot of calculation just for that one thing. And then there's also popularity bias. So we don't really have time to go into the math of why this is the case, but imagine if this original utility matrix, instead of 4, 5, 4, was straight up like all 5s. Very likely the predicted rating for this would be a lot higher and closer to 5. So it is quite prone to popularity bias. Doesn't account for your like very specific unique tastes. And then finally, there's the cold start problem, which is a huge problem when it comes to collaborative filtering algorithms, which is a huge reason why non-personalized recommendation algorithms exist and why content-based recommendations exist. So the cold start problem basically is like, what if we had 0 information on this user? So imagine that you are user 1, but you didn't have any information on any other item. You didn't have any prior ratings at all. This is actually the reason why a lot of these platforms try and get a sense of what you like before you fully onboard onto their platform. Like I think Netflix, they have you like rate a couple movies before you even start. That's to try and get some information from you so that they have some basis to start making recommendations on. So basically, if you had like all of these were question marks, you actually would not even be able to do this process. So cold start problem is a pretty big one. As long as you have like one thing there, you're okay. But yeah, that is a huge con of collaborative filtering. But yeah, before I get into the code, any questions? If anyone would like to see this in like written format, you'll be given links to like where I have this all written out in like text format if you want to see that.
Nice. We do have one question here. Someone asks, how does this algorithm perform in backtesting? And did they do backtesting in that competition? I don't know what backtesting is. What is backtesting?
Ooh, yeah, backtesting is sort of, I think, a different term for validating your model. So if Netflix had implemented this model, but let's say a bunch of people are complaining, hey, my recommendations that I'm getting, they're awful. So there is a bit of backtesting. We'll actually get into this when we take a look at the code. But usually there is this like holdout test set. And it'll make a little bit more sense later, but basically they're gonna assume that some of the data they have, they're gonna assume that they don't know what it is. And so they're gonna test their model using that. It's also very common for models to be refined. It's very unlikely for, even I've like done work for like smaller companies as well, which maybe don't even have like a 5-figure user base, and they still retrain and make sure that their models are tip top like on a weekly basis. So yeah, I think that kind of answers that back testing question.
This person said, I meant like take a complete matrix, take out some entries and fill in using the algorithm. Does it perform well?
Yeah, that's exactly the testing process that we're going to walk through in the code. Yeah.
Okay, cool.
Anything else?
Not that I can see.
All right. I don't think I see any either. I want to talk about specifically how, through my research, how Netflix does it, because we did talk about collaborative filtering on a very like small scale, but how does Netflix do it? Because you imagine their utility matrix is going to be massive. So through my readings, I found a couple things out. So they actually do use a hybrid of content-based and collaborative filtering. So someone asked like, can you combine the two? Absolutely. So and this is, I gotta admit, this is something I read like about 2 years ago. So if they do something completely different, I don't know. But what they used to do was manually tag movies. And so that helped with their content-based approach. If you remember seeing, or if you're familiar with Netflix and they have these like categories, like emotional TV shows, documentaries, suspenseful TV shows, crime shows. And of course they have these because you watch Grey's Anatomy, like the ones that are similar. So what I read, at some point, they actually had people like watching content and tagging all of their stuff. So this actually gives it more features. Each of these tags actually ends up being like a feature that they can use as part of their content-based approach. So where the collaborative filtering comes in is, instead of each of these being a single movie, it'll end up being a group of movies, basically based on like how they decided to group the movies together. So that's more along the lines of how they do the hybrid from what I've read. But on top of that, something else that Netflix does is they try and figure out your user patterns. And because through collaborative filtering, they found out user similarities. A single user can be represented by multiple user rows, if that makes sense. So for example, instead of user 1, 2, 3, 4, they could have ish at night on the weekdays, or ish on like all day Sunday, because like users might have very different viewing patterns depending on like the time of week, time of day, so on and so forth. So that's how I understand that they are applying this in their own way. I see a question. Are they still using user ratings on a scale or just thumbs up and thumbs down? From the last time I was on Netflix, they actually are now using thumbs up and thumbs down, I think, which basically can be it's pretty similar to this. So instead of it being, a 1 to 5 scale, a thumbs up and thumbs down can pretty much be a 0 to 1, right? 0 can be thumbs down, 1 can be thumbs up, and it just kind of like rescales this. So instead of all the predictions being, these are all numbers between 1 and 5. Instead of that, you can have your predictions being between 0 and 1. And then maybe they can do their recommendations slightly differently, say, okay, we'll only recommend things that are above like a 0.8, so on and so forth. So yeah. Anything else? Let's see. Forget if I have anything else on this slide deck. Yeah, I think this is it. If there are no further questions, let's get into some code. So just to summarize real quick before we do that, we talked briefly about non-personalized and content-based recommendation engines, and then we talked about how we do collaborative filtering with SVD, singular value decomposition. So right now I'm going to walk through some code of a very, very, very simple movie recommendation system. You'll get a link to the code within 24 hours of this session. All right. So before that, I do want to go over the data science process. So let's see. Yeah, the data science process. I think that if you were to ask a data science, or ask 5 different data scientists what they do at 5 different places, it can all be very, very different. That's because out in the world, data scientists, I think, usually work on either a part or have some overlap between data science and something else. So that's actually very, very common. But there are a couple people who have come up with more definitive, I guess, definitions. So this is one of them, the OSEMN data science process. And the data science process basically encompasses the gathering of data. It encompasses the cleaning of data, because data out there, if anyone has ever done any sort of like data entry or like scouring of like survey responses or spreadsheets, you know that data is not always consistent and clean. So data scientists actually do that as well. There's an explore step, which you're just taking a look to see what your data is telling you on an overall like general sense. And then data science also includes modeling, and modeling is where we get into the machine learning aspect. And then we interpret, and then use your interpretation to maybe help drive company decisions or help drive actionable insights, things like that. So we're going to go through a very, very simplified version of this process in creating a movie recommendation system. So we're going to use a bunch of different things here. SVD, that complicated algorithm that we just talked about, is actually built into this library. It's built into this library called Surprise, which kind of stands for Simple Python Recommendation System Engine. So we're going to code out a recommendation system using Surprise Library's SVD algorithm. We'll see how simple it is using code. All right, so first we're going to import all the things we're going to use. We're going to be working with some NumPy, Pandas, Matplotlib. This basically allows us to work with data in a spreadsheet and make some graphs out of it just so we can explore. And then here you can see we have our Surprise. Surprise is the library that houses that SVD algorithm we were talking about earlier. Okay, so first let's grab our data, right? First step is obtain, let's grab our data. Manage to find a ratings data set somewhere on the internet. You can feel free to check it out and get some information on that. When I run this code, this is what our data looks like. We have a bunch of user IDs, and this tells you that we actually have 100,000 rows, 4 columns. So we have user IDs, movie IDs, ratings. Actually, if you go to this data set, you can figure out what each movie ID refers to. But for now, let's just assume we don't have that. And then you can see what user 1 rated movie 31, what user 1 rated each of these movies. And you can see that there's some variance there. And there's also a timestamp, which some recommendation systems actually take into account when they rated something. We're not going to do that for now. Okay, so let's just take a look at the ratings that we have. This next step of scrubbing and exploration, there's not too much to clean here. Let's just assume that this is fairly clean. If not, you would actually go through some step of cleaning your data, removing like inconsistencies. Maybe in this data set, it's messy. Even though movies here are rated 1 through 5, maybe you have a couple like -5s or something like that. You want to clean those out. But we don't have to do that now. So next, we're going to do the explore step. Finding significant patterns and trends using statistical methods. We're not going to go into any stats today. I feel like we've already talked about a lot. But very, very simply, let's just take a look at what our data is looking like. So this basically shows us a value counts of our ratings. Actually, let me show it to you in graphical form. This is basically what our data looks like. Number of ratings and the actual rating itself. So what this is saying is that 4 is the most common rating. In this file, we happen to have 0.5 values as well. And so roughly about 15,000 people rated 5s, roughly almost 30,000 people rated 4. So this is just a very, very brief exploration of our data. So based on this, we do expect a lot of our predictions to average out between 3 and 5. Just for the sake of it, we can do a little bit more graphing just to see. So these are just a couple other graphs. Number of reviews per user. There are some users that apparently have rated close to 2,000 movies, but most of them you can see sort of hover around like the 100, 200 range. Another one we can see, review frequency per user. Most users have, let's see, around 1 to 2 reviews. You can do the same thing on the movies end. And you can see that there's 9,000 movies in this data set, and the average number of reviews per movie is 11. And you can do as much exploration as you want on this data set. But we're going to get straight into the modeling portion. Okay, So there's some lines of code here. If you're not familiar with this, don't worry at all. I'll tell you all what each line is doing. There is some documentation on how this library works. I've linked it over here. But all we need to do is we're going to use this table of, actually, let me just print it out here. We're going to use this table of information. So we're going to use this data. We're going to use the user ID, the movie ID, and the rating. It's not exactly in the format of the utility matrix that we had, with like all the movies on one end and all the users on one other end. That's because if you're storing like all of these, 9,000 movies, is that what I said earlier? 9,000 movies, and how many users have we got? 600 users. It's going to be a pretty big matrix. It's actually more efficient to store your info like this, but within the algorithm, they're going to create the utility matrix for you. So all you have to do is just feed it in the data in this format. So that's what we're doing here. We're telling it what our data is in this line. We're going to give it a reader object. And this reader object just teaches it how to interpret these specific numbers. And then we're going to load in our data set as well. And with that, that is how we take this data and have Surprise understand what our data is. Next, we're doing a train test split. Earlier, we had a question about like that back testing and how we can figure out, like, take some of the ratings that we already have and then see how well our model predicts. We'll talk about that in a little bit. But we're going to take all of our ratings and we're going to do what's called a train test split. So usually what you do in machine learning to make sure that your model is working well and not and honestly, not pigeonholing. I think someone had a question about pigeonholing. To make sure that it's not pigeonholing to that specific group of data, you do what's called a train test split. So you just assume that 20% of your data, and you see how this is test size 0.2, you're assuming that 20% of your data, you're going to assume that you just don't have it. And then you're trying to make predictions on that 20% to see how close the predictions are to your actual values. And that's what the train test split allows for. So you're only going to train your model. You're only going to show your model 80% of the stuff and then say, okay, if you've learned 80% of the stuff, based on the 80% that you know, how well can you guess on the other 20%? So that's why we're doing a train test split. All right. So you'll actually see training the model is literally just these like 3 lines over here. It's pretty incredible. So first, what you do is you're going to create a model. And within this library, it already has SVD for you. So this is how you create an empty model. And then what you do here is you take that model that we call SVD in lowercase, we fit it to our train set. So we're going to give it that 80% of data, and it's going to do all of the math that we talked about earlier. It's going to do that, like set 1 to X, figure out what the best value is over and over again. So when I run this, you see how it takes a little while to execute, like 1, 2, 3, yeah, about 5 seconds to execute because it's doing all of that math on that data set. The model has been trained. And at this point, we can actually take a look at our test set. Let's run this, and then I'll talk a little bit more about what's going to happen here. So cool. This prints out our RMSE, and this RMSE actually stands for, on our test set, those 20% of values that we had, the model did not see, but when we made a prediction on the test set using the information about the 80% that the model knew, on average, it was 0.89 stars off. So 0.9 stars off, which I think is pretty good, especially for the fact that we only trained this for not like 5 seconds. So let's take a look and see what we have here. This is us testing the model, but let's take a look at these predictions. Hopefully these are not the worst. So let me make this a little wider so it's all in one line. Okay. So in our randomized test set, so when you do the train test, it's important that it's random. We're going to see here that for user number 547, item number 72169, the real rating was 3 and the estimate was 2.75. So for that specific movie, it was only 0.25 stars off. That's pretty good. In other cases, they might not be as good. Let's see, for example, over here, the real rating was a 1, but it estimated a 2.71. So that's like a good 1.7 stars off. So it does fluctuate a little bit depending on, maybe For the ones with fewer error, with a lower amount of error, maybe that user just has more information there. Hard to say, especially when these, this like gradient descent process is going over and over again. It does become a little bit opaque. But yeah, it does fluctuate at times, but overall, on average, about 0.9 stars off. And just like that. And like, I think when we got to the code, it wasn't even like 5 minutes. We have a recommendation engine. So really quickly, we can test it and we can assume that we know like the users and the items. So let's say you know that you're user number 5. You can actually use a predict function to figure out what you would rate movie number 100. So you can pretty much plug in any number for user to be from 1 to 671. You can plug in any item number from 1 to 9066. And for any user item combination, you come up with a prediction, which is pretty neat. So here, user 5 item 100, your estimated rating is 3.624. Unfortunately, we don't have who this user is or what this movie is, but you can pretty much do this for any number here. So as long as it's under 671, maybe we can do, I don't know, 345. Here we can do something like that. And you have another prediction. So you can imagine when you have all of this data stored, you can just sort your movies and recommend the best ones. But yeah, that's all I had to share for today. What other questions do we have?
Cool. We got one question here. Can you bias your results by choosing a bad train test split schema?
Absolutely, yes. That's actually something that we talk about pretty in depth when we get to machine learning in our course as well. Yeah, if you so happen to have a randomized train test split that maybe all of your 1 ratings just happen to be in your test set, it really does bias how the model trains. A process that we use to mitigate that is called cross-validation. And what you do is you actually do multiple train test splits. And you just see, are there big fluctuations in your modeling results? So let's say with one particular train test split, wow, your model only predicts like 0.1 stars off. That's great. But on like your test set, or maybe on like a different train test split, the same model does really, really poorly. So that is something that you can do to mitigate that. That's actually known as overfitting. So yeah. We went into the pros and cons for collaborative filtering. What are the pros and cons for content-based recommendations? Going back to, yeah, we mentioned it super, super briefly, but basically main pros and cons for, let's go back, for content-based is you can get very pigeonholed with content-based recommendations, especially if you don't have as much data. So that's like, it can be a pro, can be a con, but you end up with that pigeonholing of recommendations.
Yeah, I've dealt with that when I went on, I had like another Gmail account and I went on YouTube and I looked up one thing. I'm not even like a huge wrestling fan. I looked up one thing in wrestling and all my recommendations were like The Rock, Stone Cold. It was just all of this stuff. And I was like, I didn't even ask for all this.
Yeah, I know like the WWE, that YouTube channel, they are like one of the biggest, they're I think like top 20 YouTube channels on YouTube. And I think because one, they have a lot of content. And then also they're pretty good with like how they tag their videos as well. And they've sort of like gamed the system like that.
Yeah, got some smart people working over
there. Let's see. How long have you been studying machine learning and data analysis? Where do you recommend starting? So I guess my background, I started Flatiron School's program at the end of 2018. So that's like 3 years ago, roughly, a little under 3 years ago. Prior to that, I did have an econ major, which was kind of quantitative, but I had zero coding experience when I joined this program. Upon doing the program, I fell in love with machine learning, been like continuously studying machine learning ever since. So maybe about like 2+ years. And where do I recommend starting? I would say specifically if you're interested in implementing machine learning. As you saw that with this code, I just had to figure out what to code in here. I actually did not have to figure out a lot of the math that goes behind this model. And I could implement just like that. So if you're more interested in implementing, start with Python, I think. There are a lot of like Python tutorials. Our program does a good Python thing, I think. So start with Python, getting used to coding and getting used to like reading documentation and libraries. Because once you do that, you'll be able to just look up, okay, is there a library for this kind of machine learning? And you'll be able to just plug in your data and use it. If you're more interested in like actual machine learning theory, it is important to get into math. We do talk about calculus a little bit, but yeah, calculus, and if you want to like create your own machine learning algorithms, definitely calculus is going to be important. I'm guessing any tips for success in the bootcamp. That's how I'm going to interpret that. Let's see. Bootcamp is very, very intense. I did like a full-time program, and so that was like 15 weeks, and burnout can really happen. I think the main advice that I now give to students is be okay with not understanding everything as you're getting your material in. So like we move at a pretty fast pace. The material that we cover is like, it encompasses like 3 or 4 semesters of like college work in like 3 months in a single semester's amount of time. So I think especially for like a fast-paced boot camp, if you're in a fast-paced boot camp environment, being okay with not understanding everything right when you get the information. I mean, I also identify as like a completionist. So like, it was very hard for me to like, okay, I need to move past this topic, even though I don't understand exactly what's going on right now, because it'll come with time.
Yeah, completely agree. And you know, we just launched this flex program that gives you some options. So, you know, if the 15-week feels a little bit too aggressive, or maybe you just don't have the capability based on your schedule to actually do a full-time program, you can do the flex option, which is you can do it in 20 weeks, you can do it in 40 weeks, you can do it in 60 weeks. I myself, I work as I told you, I'm the marketing program manager here, but I'm also a part of the flex program. So I'm a 60-week student. So and obviously like working here full time, I needed the option that was the longest, that gave me like the longest runway to be able to finish the program. So I chose a 60-week program because that allowed me to really take my time and do it. So, and you said you identify as a completionist. I identify as a slow learner. So I take long to grasp things, but once it's stuck in my head, it's stuck forever. So I need the time to actually like sit with something and really think it through. So and another tip I would say, it actually goes back to something you mentioned Ish, about burnout, is like know yourself before coming in, because I think sometimes I've seen some students bite off more than they could chew in the program, and didn't necessarily like approach it strategically based on the workload. So like myself being a slow learner, I know that I would have to prioritize the things that are most important to learn, because I don't have the capacity to try to learn everything. So I think it's super important to know yourself and know your strengths and weaknesses coming into the program. So therefore, when you come in, you can really lean on your strengths and work on your weaknesses during. What courses do you teach, and what would you recommend for a high school student who may not have been introduced to high levels of math yet? That's a good one, Ish.
Yeah. So I teach the data science program, which includes Python, a little bit of statistics, basically whatever statistic that you will need to understand machine learning, and then like the very specific math that you need for understanding machine learning. What do I recommend for a high school student? I would say if you're more interested in becoming some sort of coder in the future, I think, and I loved math as well. My other major is also in math, but I do think that getting used to coding first is more value added, because now if you're in high school, and I also identify with this, like high school, a lot of things sound very interesting. Getting used to thinking analytically and in a coding sort of way will allow you to be much more versatile in the future. So maybe you don't like data science, maybe you're more into software engineering. That just having any experience with learning how to code will be able to bring you to all different directions. So I do recommend like maybe picking up Python. There are a couple other languages. Maybe do a little bit of research on what kind of coding you would be interested in. And then go from there. Python is one. I know our software engineering course does, I want to say Ruby or a little bit of JavaScript. So kind of up to you and figure out maybe like I myself, when I was first picking up coding, I did look at a bunch of other languages and Python to me looked the most intuitive. So I went with that. But yeah. What is the difference between data science and software engineering? To grossly generalize, data science is more doing machine learnings, doing like predictive algorithms and stuff. Very little front end, as in like we don't code out websites and stuff like that. Software engineering does more like apps, websites, more like front facing stuff.
Yeah, I would say just to add on to that, like think of a data scientist as someone that's trying to solve a particular business, government. I don't like to just go straight business problem, but like an organizational issue. They're trying to sometimes, even in like data for good, you're trying to figure out like what the actual problem is. You're trying to help allocate resources. You're trying to help inform decisions based on data. And whether it's current or future decisions with predictive modeling, with software engineering, more times than not, you're building a product. You are actually developing a full-fledged interactive product, more times than not for public use. For data science, I would venture to say like most of the times it's just for the company. That's like more proprietary stuff. Like in sports, I was watching a documentary on a particular woman who was a data scientist for a basketball team. And she was speaking about some of the work that she does. And then at a certain point, she said, this is as far as I can take it. Like, I can't tell you anything else because everything else now is like proprietary stuff. So I can't speak on it. So I think that's a major difference as well.
Very, very true. Yeah.
Got a few more. Hold on, I got to scroll up.
I see one. The Jupyter notebook, will it be available after the event? Yeah, you'll get it in a link in your email. That's an easy one.
When you publish your work, is it a standalone service or is it included into a regular backend software service?
I think depends on the context. So
yeah.
I've written algorithms for other companies before. And then, yeah, I guess it is integrated with an app. I've also done like more on the side of like, I want to try out my own fun mini project, which I've done for fun as well. And then in those cases, it's just on GitHub, honestly. That's, I guess, what you can mean by publish. But as a data scientist, most of the time, your algorithm will be used as part of a company's process, maybe in like decision making, or maybe even in an app. Like if you're doing a recommendation system, the outputs are things that users are going to see. So yeah, it really does depend on the context.
It's true. How useful is machine learning in college when it comes to being able to do practical application with machine learning?
Ooh, that's a good one. I actually thought about this a lot because I learned machine learning first through this program. And then my eventual goal was I want to be able to write these algorithms from scratch on my own. And so I actually took a couple like college level courses or grad school level courses in machine learning afterwards. So I think that if you're doing like machine learning research, the implementation is actually the easier part. As you just saw, like we did this in like 2 minutes. So implementation part is easy. Even if you're like coming up with a new algorithm and you're coding it out, that's still the easy part. I think there's a lot of time and effort that has to be put into like fully understanding. Like that slideshow of like how I broke this down, this took me like a good amount of time to like be confident in understanding how this worked. So I think if you're like starting with the research, implementation will be the easy part.
That's a good point.
So I want to talk about this like graph systems one just real quick.
Go for it.
Yeah, graph systems, so interesting. So it's one really cool implementation that I've seen is like related products. Like, how like on Amazon, I guess if you buy a plant, they will also recommend like watering cans, I don't know, potting mix and things like that. So they kind of use graph systems. I don't know if Amazon themselves uses graph systems, but that's like a whole nother field of math that's like completely separate from linear algebra, completely separate from calculus. And so, I think it's super interesting. And then for model outputs, they are usually saved in some sort of cloud server. Either they do that or it's actually using the model live. You don't have to save it anywhere, but yeah.
Cool. Do you have to learn a specific programming language or is it open to any?
Or let's see, specific programming language, I would say like for data science, it used to be like Python or R, and R leaned very heavily for like, to my knowledge, R is more for like the more academic, I guess. I do think that now it is leaning very heavily to Python just because it's easy to implement. So I do think that Python, if you really want to get into like this kind of work, Python is the one to go for.
I've seen R used quite a bit in finance too. That was the only area.
Mm-hmm.
I've seen it quite a bit
more like the traditional industries.
Yeah,
for sure.
kind of like the legendary, the ones that have like a lot of history behind it. Yeah.
Mm-hmm. And R is hard. I've tried.
It's funny. We had a student one time that came back for an alumni event, and someone asked her like, "What makes Flatiron School so good?" Right? And she said, "Well, here you get to learn how to learn," because she went on an interview for a job in finance. All her projects were done in Python. She came into work day one, and the work was in R. And she was like, well, I didn't learn R. And she brought it up to the manager and she said, hey, just give me a couple weeks and I'll be proficient in it. And it was because she learned how to learn, learning from scratch how to learn Python. She kind of just implemented those same fundamentals, and in no time she was programming in R. And at that time she was there for like a year and a half at that point. So wow. Yeah, it was a super, I wish I said I planned that story for that event, but like it was incredible to see how like she was able to kind of get around that situation.
That's awesome.
No more questions. Okay.
Cool. In the email, you'll get like a link to this stuff. And let me actually show y'all what it will look like. You'll get a link that looks like this. And then there's a couple ways you can do this. You can actually just click this and you'll see the code. Or if you're familiar with like Jupyter notebooks and all that, you can click into these as well. And also I've linked my own personal information if you want to reach out, connect with me on LinkedIn. Happy to like chat about whatever.
Cool. Well, thank you again, Ish, for another wonderful workshop. Thank you.
Very welcome.
Yeah. Thank you everyone for joining us tonight. Again, recording will be available. We'll send a follow-up email with some resources along with this code and the recording and stuff. And that's it. Have a great one. Hope to see you on campus at some point. Hope to see you at another event, and have a great day. Great night, wherever you are.
Bye, everybody.
See ya.